types of spectroscopic measurements, whether they may be based on optical, UV, IR, X-ray, and electron spectroscopy. There are mainly three types of processes that take place. One is related to absorption, or it could be also called transmission in the case of thin samples. Another is reflection, and the third one is emission, based on which you can also have luminescence or fluorescence. So the kind of setup that one can have is, if your source, it may be either pulsed or it can be continuous. It is interjected by a polarizer, and then you have your sample which absorbs the source light, and then you have another polarizer to get the information, and finally your detector. Else you can have a reflection, a collection of the reflection of the source input beam, either at grazing incidence or an emission near in the perpendicular direction, in which case once again you have a set of polarizers at the incident and at the output side, and finally a detector. And for any system, if it absorbs a particular energy, then there are several things that can happen. The electrons can get excited from the lower valence band to the conduction band, and upon de-excitation, it can lead to a transfer of its energy to other intermediate vibrational levels of the system, and then thereafter it can cause emission. So this is typically an absorption spectra of versus the photon energy for gallium aluminium arsenide and gallium arsenide quantum well system. So the main types of information that can be obtained from such experiments are related to the energy differences between various electronic and vibrational states of a particular molecular system or any other atomic system, or it is related to the rotational quantum energy states of the atom. Third is, it is also can be related to the lifetime of the excited states and their energy relaxation channels. So the important considerations when performing such spectroscopy experiments are related to the spatial resolution of the radiation which is incident upon the sample and propagates within the sample. The wavelength or the energy resolution of both the incident radiation and the detected radiation will determine the overall spectral resolution. The intensity of the reflected, transmitted, and emitted radiation may be recorded as a function of the wavelength of the incident radiation. This is one thing one can do. Or else, the wavelength of the incident radiation is kept fixed, and the distribution in the intensity of the reflected, transmitted, and emitted signals are spectroscopically analyzed as a function of wavelength. So there are two things: either you vary the wavelength of the incident radiation and monitor the changes in the intensity of the reflected, transmitted, absorbed, and emitted radiation, or you keep the wavelength of the incident radiation fixed and notice the changes in the intensity of the reflected, transmitted, and emitted signals as a function of this wavelength. Now, what are the various components for the optical spectrophotometer? There are different types of excitation sources that you can use, like the deuterium lamp, tungsten lamp. For UV, for UV vis, you either use lasers or X-ray tubes. For X-rays, of course, you use the X-ray tube, and you can also use the mercury lamp or the xenon lamp also for UV vis type of spectrophotometers. Then you also additionally use something called the monochromators, which help you to filter a certain wavelength range that you are interested to work with. So these monochromators are based either on filters or gratings plus a slit or prism. They have a similar job, the three of them, to select a particular radiation, a particular wavelength of the radiation. Then for detectors, you have a wide range of detectors that you can have. One is a photomultiplier tube, or you can have CCD cameras, which is charge coupled devices, or photodiodes, thermocouples, or the pyroelectric detectors. So for any spectrophotometric method, what you need to understand is the interaction between the light and the matter. So which can be of various types: absorbance related, excitation, emission, luminescence, fluorescence, and phosphorence. These are the various types of interactions that can take place whenever light interacts with matter. And the main components of the spectrophotometer is, one of course is the source, the other is the monochromators, then the detectors. You additionally sometimes have interferometers, gratings, and so on. Then there is an important law which is called the Beer's law, which helps you to analyze the absorption of the light intensity. The mechanism and the application of this UV vis we will look in our subsequent slides. So for any frequency scanning techniques, there are few definitions that one must be aware of, which is what is the emission method, that is the source of light is the sample here. And absorption method, intensities of the source with and without the sample in place are compared. And next, the spectrum is finally a plot of the intensity versus frequency or wavelength. So this here slide shows you the regions of the electromagnetic spectrum that one can probe at. So starting from X-rays, of course one does not use gamma rays for this kind of investigations. So we have here X-rays whose wavelengths are very small but have very high energies. These are associated with bond breaking and bond ionization. Then you have the ultraviolet wavelength of light, which is responsible for the electronic excitation of various states, vibrational states, rotational states. Okay, so these are generally actually these ultraviolet are more related with only electronic excitations by absorption, while as beyond visible wavelength range, if you're using infrared and microwave, then what you are looking at are exciting the vibrational states of the atoms or the rotational states of the atom. That is, any atom at a particular room temperature will be undergoing a set of various types of vibration relating to stretching of the bonds or bending of the bonds. So these are all related with infrared Raman spectroscopy. So this gives you the range of electromagnetic spectrum for the light that we can employ to detect various types of events for a particular molecule or atom system. So this graph here shows you the electronic structures for simple molecules. So if you have here, this is the green curve here, for instance, represents the ground state. This plot is basically a plot of the energy versus the distance or the bond length. So this resembles your Lennard-Jones potential, where this green curve represents the ground state, the blue curve is the excited state corresponding to singlet, and the orange curve corresponds to the excited state triplet. So each of these lines here correspond to different energy states occupied by the electrons. So when the electrons are excited, given energy, external energy in the form of photons or electrons, then they can get excited and to higher states as represented by the excited state, singlet state, and the excited triplets states. These red curve corresponds to dissociated states. Then based on this interaction of the photon with the molecule, there are several things that can take place. For instance, if you have electrons which absorb this energy and are excited to these higher states represented by this blue, then these correspond to the UV-vis absorption spectrum that we characterize when we are using UV-vis spectroscopy. Or else, if these electrons from the higher state get de-excited and come to the ground state, then they correspond to the fluorescence spectroscopy. And then if you have lower or higher wavelength that you use, then you can have certain excitations of vibrational excitation spectra which correspond to these IR Raman spectroscopy. So the different types of optical spectroscopy that one can have is UV-vis, FTIR, atomic absorption spectroscopy, atomic fluorescence spectroscopy, and X-ray fluorescence spectroscopy. So we will limit in our module, this module, only look at how the UV-vis absorption spectroscopy is done. It is in short sometimes also called UV-vis spectroscopy. So these photon-based spectroscopies have actually been revolutionized due to the advancement in the type of radiation that one can incident on a particular system. So it is one such radiation is called the synchrotron radiation, which are highly monochromatic wavelengths of light that you can use to probe certain selected regions of the spectra. The other is when you're looking at optical or UV regime, the advancement in the availability of lasers which provide coherent, intense and tunable radiation has improved these spectroscopy techniques. Furthermore, some of these lasers can be pulsed over sub-picosecond time scales. So one can do spectroscopy called the femtoscale spectroscopies, where you can monitor events up to the time scale of 10 to the power minus 15 seconds. So that is a really time scale. You can actually monitor the chemical reactions that are taking place. For any optical measurement, there are two simple optical measurements that can be done. One based on reflectivity and the other is transmission or absorption. Both these techniques record either the reflectance or the transmittance / absorbance as a function of the wavelength. For transmittance measurements in the wavelength range is approximately 185 to 3000 nanometers, and there are nowadays many types of dual beam spectrophotometers available where one can change from the UV region to the visible region, such that one can scan the entire UV to visible range, and that is why the technique is also called UV-vis spectroscopy. So now we will specifically look at the UV vis spectroscopy. UV vis absorption spectroscopy, where let us consider a molecule of any material. It has certain internal energy which can be considered as a sum of the energy of its electrons, the energy of vibration between its constituent atoms, and the energy associated with rotation of the molecules. Now, if you are looking at simple molecules, the electron energy levels for simple molecules are widely separated, and usually the absorption of a high energy photon, that is one with very short wavelength, can excite a molecule from one level to another. In the case of complex molecules, the energy levels are more closely spaced, and the photons near ultraviolet and visible light can affect this transition. Therefore, substances will absorb lights near ultraviolet region and visible region, and that is why this type of spectroscopy is also called the UV vis absorption spectroscopy. So if you take a metallic nanoparticle system and look at its absorption behavior, you find that the absorption behavior for these metallic nanoparticles is dependent both on the size and the shape of the particles. So why is that? This first explanation was given by me, who solved the Maxwell's equation for the case of a spherical particle. And the reasons for the size and shape dependent absorption property of the metallic nanoparticle is on account that in the visible region, an excitation in the visible region corresponds to the excitation of surface plasmons by the incident electromagnetic radiation. And what are surface plasmons? Surface plasmons are nothing but collective oscillations of valence electrons associated with the surface atoms. So if you are looking at bulk materials, these surface plasmons are relatively insignificant in the spectra, but they become a very important phenomena in the nanometer sized particles on account of their large surface area to volume ratio. So on the basis of this, you have a technique which is called also the surface plasmon resonance spectroscopy. And if the particles are not spherical but rod-like, for example, then the plasmon absorption will split into two modes, namely transverse and longitudinal mode, corresponding to the electron oscillations perpendicular and parallel to the major axis of the rod. So on account of this shape variation, you get different kind of absorption spectra or peaks in your UV vis spectrograph. So the absorption technique, what does it involve? It basically involves a measurement of the attenuation of the intensity of monochromatic light as it passes through the sample. So at a given wavelength or frequency, the relative absorption intensity I versus I naught generally follows this Beer-Lambert law given by this expression, that is the absorbed intensity divided by the initial incident light photon intensity is equal to exponential of minus kx, where k is the absorption or extinction coefficient and x is the path length of the radiation through the sample. So the light source can be, as I said before, it can be either a tungsten lamp or a gas discharge lamp, or it can be a highly monochromatic continuous laser or a pulsed laser. So the type of experiments that are possible are that you can probe the change in absorption following the absorption of a laser pulse. The absorption can be measured by monitoring the intensity of the transmitted beam directly, or by measuring the absorbed energy in the form of heat deposited in the sample. This graph here shows a UV-Vis spectra for gold nanoparticles of different sizes. As you can see, you have various spectra corresponding to different size of the gold nanoparticle. For instance, this solid line corresponds to gold nanoparticle of 9 nanometer in dia. The dashed line here corresponds to 22 nanometer dia. Then you have another shifted solid line corresponding to 48 nanometer, and finally this small dashed curve corresponds to the 99 nanometer size particle. What you can observe from these UV-Vis spectra is that as the size of the gold nanoparticle is increasing, both the shape of this curve as well as the maximum absorbance peak is getting shifted towards the higher wavelengths. And if you plot the full width half maximum of these curves, you notice that at the point of around 60 nanometers there is a drastic change in the full width half maximum of the curve. Up until then there is only a gradual change in the full width half maximum. It is remaining this. This transition point signifies a major change in the absorption characteristics of the gold nanoparticle on account of its confinement property. So at this point there is a drastic change in the absorption characteristics for a nanoparticle which is greater than 60 nanometers. This here is the UV-Vis absorption spectrum for zinc oxide nanoparticles. Generally, for bulk, if you look at the UV-Vis absorption spectrum of bulk zinc oxide, then you get a maximum absorption in the peak at 375 nanometer. But here we see that the peak is shifted by around 10 nanometers due to the nanometric size for these zinc oxide nanoparticles. So from these changes in the absorption peak positions from the UV-Vis spectra, you can determine the change in the property of the material from bulk to nanometer. So with this we complete the discussion for the UV-Vis type of spectroscopy. Next class we will look at the photoluminescence kind of spectroscopy.